Welcome. Let's solve Leetcode 3203. Find minimum diameter after merging two trees. Okay, so we're given, let's make this bigger. Two trees, and we're told we must connect one node from the first tree with another node from the second tree with an edge. So we're connecting each tree with an edge. Return the minimum possible diameter of the resulting tree. The diameter of a tree is the longest path between any two nodes. Okay, so we're given these edges for the first tree and these edges for the second tree. So the task is to figure out how to connect these nodes that minimizes the diameter. So in this case, the diameter for this first tree is 2 because that's the farthest, that's just the farthest to go. What does it say? That's the length of the longest, the diameter is the length of the longest path. The longest path for this tree from any nodes, any two nodes, is 2. In this case, for tree 2, it's 1. So if we were to connect them, well, there's optimal places and unoptimal or suboptimal. So suppose we connected 3, 0, 1, and then 1 to 0. So that would be 2 plus the connecting node, which is 3, 4. So that would be suboptimal. Suppose we connected now 3, 0, now the 0 node to the 0 node. That would be 1. From 3 to 0 is one edge. 0 to 0 is another edge. 0 to 1 is the third edge. So that would be a good candidate for where to place the connecting edge for the two trees. So that's our task, is to figure out the minimum possible diameter of the resulting tree. That's our task. Okay, and then we just get something more complicated like this, and the result should be 5. Okay, so what I'm going to do is kind of jump to what I feel is the, what's the word, the focal point of the problem, how we should approach it. Okay, so let's look at a couple examples here. Let's make this bigger. So now suppose we have these two trees, and I'm going to make this tree a little bit bigger. Well, sorry, much bigger. So the diameter of this smaller tree is 2. The diameter of this bigger tree is, I don't know, maybe 20, it doesn't matter. So no matter, well, we could do a couple things, right? We could, we could connect the first tree to the endpoint of tree 2. But that wouldn't be a good idea, right? Because this is already 20, then we're adding 2 more, so we're making it 22. So we want to make this smaller, or sorry, we want to not increase the diameter. So it would be maybe somewhat of a better idea to place this somewhere, this first tree, and maybe somewhere along the internal nodes. So then once you place this tree, connect it somewhere the internal nodes. My point is, if this tree is big enough, it doesn't matter like the size of this other tree, the diameter of it. The answer would simply be the maximum. So if one of the trees is vastly bigger, or has a vastly larger diameter, the minimum diameter after combining both, or merging, we'll call it merging both, merging the two trees would be the maximum of the diameters, of the trees. So as you can see, we could probably merge this tree somewhere in the middle, but the diameter would remain unchanged. It would still be 20. So I wanted to make that point. So we could have that. Now, suppose, let's go back to our original tree. 1, 2, 3, 4. So we know that we can, if one of the trees is vastly bigger than the larger or the other, we can simply use the maximum, and that would be the diameter. Like, no, there is no optimal way. There is no good way to do it. That's just something we'll have to, that would be the answer. That would be the answer. So now a more common scenario, what's the word? Another scenario that may add complexity is, suppose that we don't have, the sizes of the diameters are not vastly different. So in this case, the diameter of this first tree is 2, and the diameter of this second tree is 4. 1, 2, 3, 4. So they're not too much different than each other. So then hopefully we recognize that it would be ideal to merge the trees at the center of each other. So if we're merging the trees at the endpoints, obviously that's not going to be advantageous. We'd be making it longer, making the entire diameter longer. So again, we want to try to merge the trees at the center of each other. Okay, so let's look at this tree here. The center of this tree would be, let me see, so I think right here, this would be the center. So from here, the number of edges would be 1, 2, either way we go, right? 1, 2. Now here, this is the center for this first tree. And this would give you 1, and this would give you 1. So no matter what, we have 1. So now, if we go with this approach, if we're always trying to merge the trees at the center, so no matter what, since we're merging the tree, we're adding an edge. And then the question becomes, okay, the middle of the first tree is here. So that means no matter where we go, so we know the diameter is 2. So in essence, we maybe be dividing it by 2. We would be dividing it by 2. And that would give us the one edge here, no matter which way we go. And for this guy as well, if we connect it to this here, to this node here, no matter which path we take, we know that the diameter is 4, and we would only be adding 2 to the entire diameter. So in this case, this would give us what? 2 divided by 2 is 1. So we get 1 plus 1 plus 2, which equals 4. And I think that makes sense, right? So if we're here and we connect our tree here, that's one edge. Looking at this tree, this is 2, 3, and then here that would be 4. So total of 4. Okay. So I think that's clear. Now, what makes it a little bit more challenging is, suppose though I'm going to change this tree a little bit. Here, maybe. Let's do it like this here. 1, 1, 2, 3. Let's do it. Yeah. So I'm going to change this tree a little bit. Okay, so if you notice, previously both of the trees had a diameter that were even. But in this case now, I've made the trees slightly different. So now the diameter is 3, and here the diameter is 4. So again, remember, we don't want to ever merge the trees on the endpoints. We kind of want to merge them in one of the middle, hopefully the center, or somewhere somewhere along this diameter, because this is the diameter, the longest path, we want to add it somewhere in the middle. Now, there's an issue though when it's the middle. So previously when the edges were only 2, so the middle was easy because we could just find the middle. And no matter which way we went, it was going to be 1 or 1, whichever way we went, there was going to be only one edge we had to traverse. But when the diameter is odd, we have a little bit of an issue, because if we go this way to the left, we're only adding a single edge. But if we go to the right, we're adding 2 edges. So we can't get around that. We're always going to have to go with the bigger amount. So in order to compensate for that in our formula, we need to add 1 to our diameter. Sorry, the middle of our diameter. So remember before the diameter was 2 and we divided by 2. Now we need to add 1 to it before we divided by 2. And same thing here. Well, that's just going to be just the general modification that we need. So let's go over that here. So 2 plus 1 is 3. 3 divided by 2 is 1. 4 plus 1 is 5. 5 divided by 2 is 2. And we still get 4. This was the 3 divided by 2. Yeah, sorry, I made a mistake here. Sorry, the diameter is 3 here, not 2. 3 plus 1 is 4. 4 divided by 2 is 2. This is 2 here. And now this is 5. So I hope that makes sense. All right, I'm just going to go with it. So if we're using one of the internal nodes, the best we can do is say, okay, this is going to be 2. And here, well, the best one is this, like the center of the diameter here is also 2. So 2 plus 2 and plus which is 4, plus the node to merge them would be 1. So that gives us 5. So if we think about it now, the answer will be the maximum between 3 values. Remember, either the smaller tree or the bigger tree, or using this formula here, where we use the center of the diameters to help us. So the answer would be something like the smaller tree divided by 2 plus the bigger tree divided by 2 plus the edge to merge it. And then that would be our overall answer. So I'm actually going to use that. I'm actually just going to write that down right now. So I'm going to actually just write that down right now. So I'm going to say, okay, return max of D, and then this is right down. Let's just copy it down. Max of, is that right? Okay. Now the question is, well, okay, well then, now we're stuck with, well, how do we find the diameter? And that's not too bad. But I think that's easier than this part here that we needed to go through. Okay, so let's figure out how to find the diameter now. So what we'll do is we'll start with 0. So part of the problem states that we don't know how many edges or nodes we have. So we could have 0 edges. So meaning this, look at the smallest number of nodes could be 1. So there could be 0 edges. But we're always guaranteed at least 1 node. And that node has a name of 0. So what we'll do is we'll use that to our advantage. So what we'll do is we'll always start. So we will start at node 0. So we will start at node 0. And then do what? So we'll start at node 0. And so we don't know like where 0 could be in our tree. So like, for example, the node 0 could be here, or it could be here at the end. It could be here. So we don't know where node 0 is located. But we'll just start here. Just suppose it's here. And what we'll do is we'll perform breadth first search, and we'll expand outwards to find the leaf node. So we'll go as far as we can. So eventually we'll have this here as call this farthest node. So eventually though, when we're using breadth first search, we'll reach the farthest node. So in this case, it could be this. It will be this guy because this is 2 and this is only 1. Now let's look at how this would look here. Let me just delete these. We don't need these at the moment. Suppose now we're here on the second tree. We perform breadth first search again. So we could also end up here. This could be one candidate, or it could be here, right? If we perform breadth first search, let's move this over a little bit. Now, does it matter which node we choose? Does it matter which node we choose? No, not at all. Not at all. Remember, for the moment, right? We only care about the distance. We only care about the distance. So this is 2, and this is 2. So, but in this case, we did care about the node, but we're more concerned about the distance. So let me slightly modify that statement. So we will perform breadth first search twice. First time we will start from 0 to find a leaf node. Okay. So remember, this leaf node will always be one edge of the diameter. One leaf node will give us one node of the diameter. So I hope that makes sense. So whenever we're at a central node 0 and we go out as far as we can, the very last node will be the leaf node for the diameter. There could be a tie, but that means that it doesn't matter. They're at the same length. So I want to make that clear. When this first BFX breadth first search ends, starting from 0, that node that it ends at, or one of them, will be the node on the diameter. Or a diameter, because there could be multiple diameters. And then secondly, the second BFS. So where do you think we should start with? Well, what we'll do is we'll start from the farthest node from BFS 1. Okay, so remember, so let's suppose we were here and we did BFS and we found this node. This was our farthest node. And then, okay, then we perform BFS starting from this node and we go all the way out. Then we notice that the last node is, that's the diameter. So I hope that makes sense. So we start here from 0, we go to the farthest node. Sorry, we find the farthest node on the first BFS. On the second BFS, we start at the farthest node, and where we end is the other end of the diameter, which will give us our length. And we need that length to compute this here. Okay, so I hope that makes sense. We start with the 0. First time we start at 0 to find a leaf node. The leaf node will give us one node of the diameter. The second BFS will start from the farthest node from BFS 1 and give us the other node of a possible diameter. But at this point, we only care about the length of the diameter. So once we only need to find the actual value, because remember, when we're finding our answer, we only care about the value. We only care about the node on the first BFS because we want to know where to start with on the leaf node to find the second leaf, other end of the diameter, and then that's going to help us solve this. Okay, I hope that makes sense. Otherwise, I think that's enough to get started. Okay, so let's write a couple functions to help us. So I'm going to write two functions. So what we'll do is, well, let's figure this out. So I'm going to write this node called maybe, so D1 will be the, or D will be the size of the first tree. And we'll call this equals, I'll call this explore. Actually, I don't even know if I need that here. Actually, just I'm going to do this here. We just care about this here, explore. Yeah, we just care about the diameter length, so we don't need anything else. So explore will take edges 1. So what we're going to do is we're going to pass in the graph, and the first graph will look, you know, something like this or whatever. And we want to build it and find the farthest node, and we want it to return the diameter. Okay, and then we'll do the same thing for the other node, for the other tree. Call explore, and we'll pass in the other edges. Okay, cool. Okay, so let's write explore. So explore needs to build the graph. So explore, it will accept the edges. Okay, so then remember though, it's possible that there could be no edges. So if there's, suppose n is 1, that means there's no edges. So we can just, we need to account for that right now. So let's say, okay, if not e, return 0. Okay. Otherwise, let's start with creating our graph. So let's use a default dict, so we can add our neighbors. List. Okay. And then let's run through our edges. So for u comma v in e, we'll say, okay, gu dot append v, and then the same thing for the other node, because it's not a directed graph, it's undirected, so we can go either way. Okay. And then what do we do next? Well, remember we need to conduct 2 breadth-first searches. So let's just find that maybe. So let's just call it breadth-first search. So okay, so we'll say, okay, run breadth-first search, and we need to send it the graph, and we need to send it the node to start with. And what will it return? It will return the distance, and it will return the farthest node. Okay, so we'll call this far node. Okay, far node, or yeah, it's fine. Farthest node. And then remember, we'll run it again, and we'll get a second distance. And remember, though, this is the distance from this node to the diameter, but that may not be the entire diameter. So we're going to run it again, and this will also be a far node. We don't really need it, but at this point we don't need this far node. But well, in fact, we don't need it, so I'm not going to use it. BFS and same graph, but now we start at this far node now. So we started here, far node. And once we have that, once both of them are done, we say, okay, return. So remember, this is, let me go back to this up here in case you forgot. So originally we started here at 0, and we ended here at 2. So at this point, imagine this would be 2. But then now we start at this node, farthest node, and then we say, okay, 1, 2, 3. So then this guy would return, 3. So it's more important that we return this guy. So we will return D2, and that's it. Return D2. Okay. I think we're good so far. Now we need to define our breadth-first search function. Okay, no problem. So define breadth-first search, and we passed in the graph and the starting node. Pass in the graph and the starting node. Okay. Okay, so what we'll use is a deck, a double-ended queue. to hold our starting, sorry, we don't want it to be 0, it's a node. So we put a node here, and we'll just put it, call this Q. Okay, looking good. And then we don't want to explore the same node twice, so we'll do something like, we'll add a visited set maybe. And so V will equal zeros. So 0 means it has not been explored yet, times the length of G. And we'll set the first node equal to true. And lastly, remember breadth first search, we want to count how many edges we've gone through. So when we go here, this would be our first level, and then for every level we need to add to the diameter count. So what I'm going to do is I'm going to say, okay, let's do maybe I'll call this like max path, and we'll set it equal to 0. Right now it's 0. And then now we perform our breadth first search. So we say while Q, and then we need to only go by the number of nodes on the layer. So currently there should only be one node in that layer. So okay. So we say for, we don't really care about how many nodes there are in there. So we're not, the index is index wise. So then we pop the node. So we say q dot pop left, and this will be the current node. We'll call this maybe what should we call this? We can call, I don't want to use the same name here. Let's call this maybe V for vertex, is fine. And remember though, what we need to do is we need to remember this node because we use it on the second breadth first search. So we need to remember this. So we'll store that here. So we'll always remember this. We'll call this maybe the max node. So yeah, so V will be maybe the current node. Maybe, yeah, current node. Let's just do this. So when we pop the node, it'll be the current node, and we just use max node. Max node is fine. And remember, so at the end we'll return that. At the very, very end, we'll return, what is this expecting? It's expecting the distance and the farthest node. So the distance, I called it max, and then here's the max node. That's at the end. So now let's resume the breadth first search. So we're at this current node, and we want to look at the neighbors of the current node. So for neighbor in G of current node. Now we only want to explore this node if we haven't already visited it. So we say if not V of neighbor. And then we can, now we'll add it to our queue, but also say that it's visited. And we'll say queue.append neighbor. Okay. So we need one small thing next. So how do we increment our diameter length? This is our diameter length. So let me just, yeah, I'll leave it as max. This is our diameter length. So diameter length, diameter. So currently it's 0. So imagine if there are no neighbors, so that means we wouldn't add, so Q, if node is 0, sorry, if this node is 0 or any node, and there's no neighbors, well, we wouldn't need to, so we need to perform a check here. So right now, this Q is saying, okay, I'm holding your neighbors. So if Q, then we add to our neighbors. We add like the, I guess the path or the length of the path. So my point is this: suppose we're here, and the neighbors of that would be added would be this guy and this guy. So that means we know that at least there's a path of 1. Okay, then we're at this node. This node doesn't have any like unexplored neighbors. We couldn't. There isn't anything else. We already explored this one, so we can't use it. So in this case, there wouldn't be any more neighbors. We would stop. But this guy says, okay, I have neighbors. So then we would add this to the queue. So then out here, that means if there's neighbors, then we add one to the queue. So we add one to our like count, our measurement. So then this would become 2. So I hope that makes sense. We need to, if there are neighbors, that means we can add 1 to our diameter length. And that's what we're doing there. Okay, it's kind of subtle, but I wanted to make sure I point that out. Okay, so I think that's pretty good. I think that's enough to, I think that's it. Let's see if I messed up somewhere. So depth first search. Okay, this should be here, and this should be here. What else? I think this is okay. Let's run it. Okay, it looks pretty good. Let's submit it. Okay, not too bad. So I just want to recap what we went over so far. I think the hardest part, at least for me, was to this formula here, this part here. We want to, what this is doing here is essentially attaching to the middle, and that's why we divide it by 2. And so we cannot so like the diameter of each tree plays an important role. So once we know the diameter, we say, okay, the middle is what we're most concerned with. We are concerned most with the middle. And as I mentioned before, sometimes the length of the diameter is even, so it's we can just divide it by 2. But sometimes it's odd, so when you divide it by 2, we need to, in essence, use like the ceiling. So this is 3. 3 divided by 2 is 1, but 3 divided by 2 is 1, but that's not accurate. That's not an accurate representation of what would happen. So this is 2. When we connect this 2 to this guy, that's 3. But it wouldn't be 4. We would add 2 here, 2 more here. So the answer would be 5. So that's why we had to use this slight modification here. We added 1 to it. In essence, like the ceiling function. Okay, I thought this problem was a little bit hard, a little bit tricky, but now that we've gone through it, I hope that it makes sense, and hopefully now the problem seems less difficult and maybe even easy, but at the very least less difficult. If you found this video helpful or educational in any way, please consider liking or subscribing. Other than that, have a wonderful day. Take care.